Here we have an important theorem. Conservative fields are gradient fields. Let F equal Mi plus Nj plus Pk be a vector field whose components are continuous on an open and connected, and I need to talk about that word connected, region D. F is conservative if and only if F is a gradient field. What this means is the only conservative fields are gradient fields. The fundamental theorem of line integrals tells us that if we have a gradient field, the field's conservative. This theorem connects the rest of it that if we have a conservative field, it must be a gradient field. Another way of thinking about it is every conservative field has a potential function for some differentiable function. The word connected. We know what it means to have an open region. So I could imagine all the points on the inside of some region like this in space. If I just consider the interior points, then that's an open space. The word connected means that if I take 2 points in the region, there is a path between them that's also entirely in the region. And so that region is connected. So would a region shaped like a donut or a squished donut like the one I've drawn, because even though I can't go straight across to this other point, I can still travel along the donut to the other point. Those are all connected regions. This theorem only holds in connected regions. Later on we'll meet another term called simply connected, which is a little different, but we'll hold on to that for now. What I'd like to do now is do a little problem that makes me think of the last theorem. So find the work done by the vector field F, which is 3x squared, comma, z squared over y plus 2z natural log of y along the path connecting 1, 1, 1, 2, 1, 2, 3. Well, my only hope to even be able to answer this problem is that this field would be conservative. Because if this field is conservative, then there's a potential function, and if there's a potential function, I can use the fundamental theorem of the line integral. So I'm hoping that this is conservative. If it is conservative, then there is a gradient. It is a gradient field, and I should be able to find that potential function. So let's try that. So if this is a gradient field, that means there's a function f of x, y, z, so that del f is, of course, that field, making these all partial derivatives. So this would be the partial of f with respect to x, which would mean that function would be x cubed plus maybe some function on the variables y and z. That would be f. Partial of f is that guy. So this is my first candidate for my potential function. So now let's take a partial with respect to y. Well, this first part would go away, and I would just see the partial of g with respect to y. Well, that would be this part. So the partial of g with respect to y is z squared over y. So to find g, this function here, all I need to do now is integrate this with respect to y. All right, so I'm going to come up here. My function f was x cubed plus maybe some function still on y and z, and I found out that that function's partial with respect to y would be this. So integrating with respect to y tells me that would be z squared times the natural log of y plus maybe some function that only would depend on the variable z, so h of z. All right, well now I take a partial with respect to z of this candidate potential function, this potential function, and this part would go away. This part would give me 2z natural log of y, and then I have the partial of h with respect to z, or just the derivative of h with respect to z, because it's just got the one variable. But what I realize is that if I write this down correctly, derivative of this is 2z natural log of y, I realize that that's all I need, that this is 0, so that this could have been any arbitrary constant, so I choose it to be 0. And there's my potential function. So f of x, y, z is equal to x cubed plus z squared natural log of y. The vector field we're talking about is a gradient field. And the path integral to calculate work would then be path independent. I'd be connecting those 2 points A and B. F dot dr to calculate the work, that's all we do. And now I know that's just the function I just found evaluated at 1, 2, 3 minus the potential function evaluated at 1, 1, 1. All right, well, let's evaluate this at 1, 2, 3. So I'd have a 1 plus 9 natural logs of 2 minus f of 1, 1, 1. So I'd have 1 plus 1 times the natural log of 1 is 0. Well, the 1's cancel. I end up just with the natural log of 2. Well, before I knew that gradient fields were conservative, I wouldn't have even been able to work this problem because I don't know what path I'm supposed to use, right? Because, well, if this isn't a conservative field, the path might matter. But now that I know I can find a potential function, that means this is a conservative field. And we can use the fundamental theorem of line integrals.